In this class, we will discuss Franck-Hertz experiment, which was performed in 1914, and this was a direct experimental evidence for Bohr atom model. In two ways, we will see how. Okay, and this was performed by James Franck and Gustav Hertz. Incidentally, this was the nephew of Henrik Hertz, who produced electromagnetic waves. Okay, this is the experimental arrangement. There is an evacuated quartz tube, and on one end there is a filament. When a low voltage filament is heated by a low voltage battery, electrons are emitted from the filament. Now between the filament and a grid, a positive voltage is applied. Okay, higher potential at the grid, and this voltage can vary and can be varied from 0 to 40 volt. And because of the positive voltage at the grid, the electrons will be accelerated to the grid, and there are fine holes on the grid plate, so electrons can pass through the grid plate and they can reach the collector plate at the other end. Now between the this distance between filament and the grid is of the order of 1 centimeter or a few centimeters, and between grid and collector plate there is a very small distance of the order of 1 millimeter or a few millimeters. Now between grid and the collector plate, a retarding voltage is applied. Okay, negative voltage at the collector and positive voltage at the grid. This is a low voltage, 1.5 volt. So that means that electrons, only those electrons having a kinetic energy greater than 1.5 electron volt can reach the collector. So once the electrons reach the collector plate, and this is a sensitive ammeter. Electrometer is a sensitive ammeter, and it can detect very small currents of the order of 10 raised to minus 6 ampere or 10 raised to minus 7 ampere. Okay, so this is the arrangement. And in this quartz tube, mercury vapor at low pressure is filled. So basically electron beam is passing through a gas of mercury, a low density gas of mercury. Now, so what is observed is when the accelerating voltage is slowly increased, okay, then the electrons are, more and more electrons are accelerated, and if the accelerating voltage is greater than 1.5 volt, that is the retarding voltage applied here, electrons, many of the electrons will be having a kinetic energy greater than 1.5 electron volt, so they can reach the collector. Okay, so as the accelerating voltage is increased, then it is found that the collector, the current measured in the electrometer slowly increases. So on the way, when the electrons are passing through the this gas, then electrons are having collisions with the mercury atoms. But mercury atoms are heavy compared to electrons. So when there is an elastic, initially there are elastic collisions between electrons and mercury atoms. So when there are elastic collisions, since mercury atoms are so heavy, okay, very small kinetic energy is transferred to the mercury atom. So the electrons can retain their kinetic energy and they can reach the collector plate, contributing to the collector current. Now it is found that when the accelerating voltage, when you slowly increase the accelerating voltage, when it reaches a critical value, okay, then there is a sudden drop in the current measured in the electrometer. So the sudden drop in the current indicates that many electrons are not reaching most of the electrons are not reaching the collector plate. So what happens to these electrons? It can be analyzed that these electrons must be losing their kinetic energy by the collisions with mercury atoms. So that means at the critical voltage, when the accelerating voltage reaches the critical voltage, there is inelastic collision between the electron beam and the mercury atoms. Okay, so what can be happening here during the inelastic collisions? Kinetic energy of the electrons are absorbed by mercury atoms. Possibly mercury atoms or the electrons, orbital electrons in the mercury atoms are excited. Okay, so anyway, when so this collision, let us say these collisions are, so initially these collisions must be taking place near the grid. Okay, so because when the electron kinetic energy reaches a critical value only, this collision becomes inelastic. Okay, so somewhere here we can say near the grid, electrons collide inelastically with mercury atoms, so they lose all their kinetic energy. So when they lose all their kinetic energy, the kinetic energy falls below this retarding voltage, okay, which will be less than 1.5 electron volt, so the electrons cannot reach the collector plate. That is why the collector current is decreasing. So again, when the accelerating voltage is further increased, okay, there is it is found that the collector current slowly increases. So what can be happening? Electrons are coming, they undergo inelastic collision, but still we have accelerating voltage is further greater than the critical value. So even after one inelastic collision, they have enough kinetic energy to reach the collector plate. That's why collector current is increasing. Now again, when the accelerating voltage reaches a particular value, again the collector current suddenly drops. Okay, so if you plot the collector current against the accelerating voltage, okay, so this is the accelerating voltage, and along the y-axis we plot collector current. This is of the order of 10 raised to minus 7 ampere. Okay. Let us say here we have like that. So x-axis I have plotted accelerating voltage, y-axis collector current. So it is found that experimentally it is found that initially it increases, and the first dip happens around 7 volt. Okay, so we will explain these things. Around 7 volt, and then again it increases. Okay, then so the difference between the first dip and the second dip is nearly 5 volt. Okay, so after that again there is a dip here, then so subsequently when you increase the accelerating voltage, there are different at different voltages, specific accelerating voltages, there are sudden dips in the current. So if we measure the separation between two adjacent dips, okay, we can take the separation from all the peaks or the dips, and we can take the average. So the average value is 4.9 volt. Okay, that means after the first dip happens at around 7 volt, we will see why it is so, and after that, after every 7 volt plus every 4.9 volt. Okay, so the difference between the peaks is nearly 4.9 volt, very close to 5 volt, and then there are subsequent dips. So what must be happening here? So in the first case we have seen when the value reaches 7 volt or some critical value, there is an inelastic collision, and there is no, after that there is not much kinetic energy to reach the collector plate, and that is why we get the first dip. And after that, when you increase the accelerating voltages, after the first inelastic collision must be happening somewhere here around 7 volt, and then when you increase the accelerating voltages, even after one inelastic collision, electrons have enough kinetic energy to reach the collector plate, so the current increases. When it reaches this voltage plus some 4.9 volt, okay, then what happens is there are two inelastic collisions. Okay, one inelastic collision happens somewhat closer to the filament. Okay, so one electron collides with a mercury atom and loses its kinetic energy, part of its kinetic energy. Then it accelerates and undergoes one more inelastic collision. Okay, and so that is why there is a dip in the current. That means most of the electrons will be losing the kinetic energy to reach the collector plate. That is why, here first inelastic collision happens, here the second inelastic collision happens, here third inelastic collision, like that. Okay, and we see that the difference between adjacent peaks is 4.9 volt. It shows that when the electron's kinetic energy reaches 4.9 volt and multiples of 4.9 volt, then inelastic collision happens. Okay, so what can be the reason for inelastic collision? Then Franck and Hertz argued that if these are the energy levels of mercury atoms, let us say this is the ground state and this is the first excited state. Okay, so during the inelastic collision, what happens is mercury atom is excited from the ground state to the first excited state. Okay, right, or the valence electron in the mercury atoms are excited from the ground state to the first excited state. So this difference, okay, this energy difference must be 4.9 electron volt. This was the argument of Franck and Hertz. So when the electrons, until the electron's kinetic energy does not reach this value, there is only elastic collision and the electrons are reaching the collector plate. When the electron kinetic energy reaches 4.9 electron volt or multiples of 4.9 electron volt, okay, let us say this is nearly 5 volt. So when the electron kinetic energy reaches 5 volt, there is an inelastic collision, okay, and there is a dip in the current. When you again increase the accelerating voltage and the value reaches about 10 volt, then electron undergoes one inelastic collision and loses 5 volt, and this electron moves towards the grid, and again somewhere near the grid it undergoes a second inelastic collision with another mercury atom, okay, and excites it. So after two inelastic collisions, the same electron undergoes one inelastic collision here and another inelastic collision here. So that is why there is a dip in the current here. Okay, so like that. So at multiples of 4.9 volt, the same electron can undergo multiple inelastic collisions, producing dip in the current. So this difference, okay, between adjacent dips shows that the amount of energy absorbed by mercury atoms during inelastic collisions must be 4.9 volt. So in this way, these dips of current at discrete values is a clear evidence that mercury atoms energy levels are quantized, or energy of mercury atoms are quantized, or in other words, there exist discrete energy levels in mercury atoms. So they did this experiment, original experiment was done with mercury vapor, but this can be replaced by any gas, and the same results can be shown in the case of any gas. Okay, so this is a direct experimental evidence of discrete energy levels of atoms. So in that sense, we can say that this is an evidence for Bohr atom model. And further, they did one more thing. They also measured, so when mercury, the valence electrons in mercury atoms are excited, they will remain in the excited state only for a very small amount of time, of the order of 10 raised to minus 8 seconds, and they will de-excite. When they de-excite from a higher energy level to the lower energy level, this difference in energy must be emitted as a photon of radiation. So when there is a de-excitation, okay, subsequent de-excitation, then maybe I will draw it here. So this happens during inelastic collision, and when there is a de-excitation from this first excited state to the ground state, then a photon must be emitted. Okay, and what is the energy of this photon? According to Bohr model, this must be E2 minus E1. Okay, already we know what is the difference between the ground state and the first excited state. This is 4.9 electron volt. So Franck and Hertz calculated what must be the wavelength of the radiation emitted. Okay, so we can calculate that here. Hc by lambda is 4.9 electron volt. So lambda is equal to Hc divided by 4.9. That is, Hc is, we know, 1240 electron volt nanometer. This is 4.9 electron volt. And if you do this calculation, it is 253 nanometer. Okay, which is UV region. So the wavelength of the spectral line emitted during de-excitation must be in the ultraviolet region, 253 nanometer. So they carefully they calculated this value, and they measured also. this spectral line they measured also what is the spectral line emitted during this process, and they get a value very close to 253 nanometer. They get something like 254 nanometer. Okay, so this is another, we can say this provides a second evidence that spectral lines are emitted during the transitions between atomic energy levels. When there is a de-excitation of the atomic electron, orbital electron, from a higher energy state to a lower energy state, spectral lines are emitted. So this is a direct proof of the third postulate of Bohr also, the origin of spectral lines. Okay, so this experiment provides two evidences, we can say. These dip in the collector current at discrete values clearly shows that there is a discrete gap between the ground state and the first excited state, and this separation between adjacent dips gives you the excitation energy. Okay, so that is an evidence of existence of atomic energy levels, and the measurement of the wavelength of the spectral line, which is equal to the wavelength corresponding to this energy difference, clearly shows that spectral lines are emitted during the electronic transitions between different atomic energy levels. So in this way, this experiment provides a double, we can say twin proof for the Bohr atom model. So this experiment was done very immediately after Niels Bohr announced his atom model. So in this way, we can say this provides a very good experimental proof for Bohr atom model. And Niels Bohr got Nobel Prize in Physics in 1922, just 1 year after Einstein. And 1921 Nobel Prize in Physics was for Einstein, and the 1922 Nobel Prize in Physics was awarded to Niels Bohr. I think both of them received the Nobel Prize in the same year, in 1922, because of the delay in delayed in distribution because of the First World War. And Franck-Hertz got Nobel Prize in Physics a few years later in 1925 for this experiment, this particular experiment. Okay, I mentioned that the first dip happens around 7 volt, right? And this is actually, in this particular experiment, this is actually happening at 7.1 volt. So the reason, so logically we can, if you think about it, the first dip should have happened at 4.9 volt. Okay, and then after each 4.9 volt, multiples of 4.9 volt. But why 7.1 volt instead of 4.9 volt? If we look at this value, see, I will write here 7.1 electron volt minus 4.9 electron volt, we get 2.2 electron volt, right? 2.2 electron volt. Now, this much energy, we can say, only when the electron's initial energy reaches 7.1 electron volt, we get a dip, we get an inelastic collision. So that means this much energy, 2.2 electron volt energy, must be used for something else. It happens because of the difference in work function of these two metals. Okay, we use one metal for filament, which emits electrons. We use another metal for collector plate. So usually this electron gun or the filament has very low work function. So that means when it is heated, electrons are easily escaped from the surface. So work function is very low. But this collector plate metal has a relatively large work function. So this 2.2 electron volt is due to the collector plate work function. That means when one electron reaches here, an electron should be released from the collector plate to complete the circuit. Only then we get a current in the electrometer or the ammeter. So in order to release an electron from the collector plate, this much energy is required. So that is why initially, only when the initial accelerating voltage reaches 7.1 electron volt do we get a dip in the current. That means this much energy is used for, that means only then these electrons are having enough energy for inelastic collision. Okay, this 2.2 electron volt energy is used for this work function. Okay, after that then after this initial dip, then the next dip happens every 4.9 electron volt later, okay, or 4.9 volt later. So that is why we need an initial extra 2.2 electron volt, which acts as the work function of this collector plate metal. Okay, so that is all about Franck-Hertz experiment, and this was a very important experimental evidence for Bohr atom model. Okay, that's all. Thank you.